Hello, my name is Oleg Marichev, and I'm working in Wolfram research 32 years, and I will continue to talk about integration. Right now, today, I will talk about very important Mellin-Barnes integrals. These integrals looks very difficult because they are contour integrals. In this case, integration from minus infinity starting in imaginary infinity to up direction. This function under integrand include a lot of gamma functions. Also we have z in degree minus s. This compact form very often used for definition.
Recording in progress.
Meyer G function and Fox G functions and some others, particular cases of these functions. I will explain teeny moments how to operate with this horribly looking object, how to evaluate it, and I will tell about asymptotics of this generic function. Before doing this, I will mention a little history, how this Mellin-Barnes integral appeared. At first time, it was happened in research of Pincherli in 1888. Then Mellin and Barnes studied this, and Dixon Ferrari studied later on, and after this later in 1940s, Meyer introduced function using these representations. I will tell about this below, but now I say the following. This function is very, very important because practically all significant and important functions which human civilization introduced and widely used, I'm talking about exponential, Legendre, Gauss, power functions, and so on. All these functions can be somehow representable through these integrals. And list of these functions I will give below. In mathematical notation, it is more than 100 names. And here you see Slater style definition with some kind of musical construction A, B, C, D. So we have here A gammas with construction here plus alpha. Alpha usually 1 very often. And then B function, product of B function with construction including minus, and these coefficients alpha, beta, gamma, delta positive, real numbers. Then C and D. So again here, parameters A, B, C, D. It's easy to remember, and coefficients alpha, beta, gamma, delta. But if you try to look on Meyer's G function below, you will see it. You see that it was organized in rather crazy manner, and I will explain later why it was happened. Instead, vertical line contour can be loop starting from minus infinity, going through all poles of gamma functions, and then return back to left. I will show picture of this. Let me show picture of this contour from my first book, published in how many? Already 45 years ago on Russian, and that now it is published on English. 40 years ago it was translated. People can see. Okay, contour, it can be, this is, I match left poles and point minus A, 1, and so on, minus AG, minus A, capital A. So left poles starting from this and has period 1 and goes to left direction. And here starting and goes to left, goes to left. The same for right poles, starting and goes to right, in points B, G. I mentioned these poles B, G. In some sense, if we have poles going to left, just demonstration, and going to right, we can place vertical line between a vertical strip between them if they on distance between somehow. But if we have situations like this one, poles integration should go in such way, otherwise function is not well defined. This is a contour, and vertical line, sometimes straight line allowed, as I told. Here we have strip, and inside of this strip we can take a vertical line integration, and this right loop starting in this infinity goes to here, and then goes to again goes to right infinity. This is left root, starting from here, goes surrounding left poles and goes to this area. It sounds very difficult to understand, and I will show examples for beginning. Example is the following. We can take gamma function, only one gamma function. This gamma function, oh, sorry, it is example here, example. Take one gamma function only. This is poles in point minus k with integer positive k, and this gamma function, only one, and if we evaluate this integral, it will be exponential function, which we know. And here I demonstrate how to evaluate this for more complicated case. We solve equation that gamma from this equal minus k, we find S, and then we evaluate residues of the integrand function, and we in Mathematica has opportunity to do this. It works on, and we have this sum of residues, and then we apply to some to as summation of this expression gives our exponential with factor. Now, in particular, if we have coefficient equal 1, this is 1, this is also 1, but here a equal 0, we have case which I demonstrated. It will be only exponential without any factors. Yes, I show this formally without explanation too much, but below I will demonstrate proof of such approach. And here I demonstrate one more example, this example, but in style, formal style. So each of you can take this expression, substitute S, but we need to have gamma 1 here to freeze, don't evaluate. Then we change this gamma 1 to such coefficient. It is residue, and we get this one. And after this summation, we come to already existing expression. Similar we can do if we make expression with minus s. With minus s, we do the same. And here we should take minus residue and get summation, and we come to similar result. Okay, let's return back. Here I can say that we have very important characteristics. This A, B, C, D, we should build values like how many here gamma function, how many here, and together A plus D, and the same B plus C. And these characteristics is very important, as I tell below, for choosing direction. We should take integration through left residues or through right residues. It depends from value of this construction. But I am talking about situation when coefficient alpha, beta, gamma, delta 1. Also, we have important characteristic A plus B. It means how many gamma function in numerator, and this how many in denominator. And here we have characteristic connected with exponential function. Again, it is characteristic it regulates existing sector of analyticity and opportunity to make analytical continuation residues from left poles to right poles. But about this I will tell below. One more important moment. In literature, very often you see instead z minus s, z in degree plus s. It is reachable if we change s on minus s. This guy converts to this guy, and so on. But such change here produce constructions like this one. And we cannot say that no problems with such change. If we verify this value for negative z, we have different values. Because we should not do generically for all z such transformation. These functions which not equal, but we can look where not equal. We apply such a simple check. I recommend to use this check. Of course, you can apply more often. For example, here you can try something like 16, and here 32, 34, it does not matter. And you will see positions where it is not equal 1. No, more details about such things you can find in our Wolfram function site. And in principle, all this demands special talk about two worlds of mathematical functions, which appeared, second world appeared recently when we civilization started to develop computers and apply computers for research and mathematical. Here I made a link and you can find formulas like how to operate with objects like this one. And here we implemented these formulas, and you see that it is not correct to make power expansions and ignore coefficients. Can be plus or minus 1. It depends from value of argument and functions. Also, if we talk about definitions for Mellin-Barnes integrals, it is important to say that we should have separability left poles, which comes from these points, and right poles should be separable. No, for example, below example, pole S equals 0. We cannot say we cannot stand a place between 0 coming from here and 0 coming from here, something. For these purposes, if we want to do something, we can and should write other representation. No, for example, we should write this function in form of such functions. And here we see that this guy can be more than 0. And we can write condition that minus 1 and rs should be more than. So this is gamma, which you see in integration, contour of integration. For this situation, we can build a Meyer-G function, and below you see in our code we can operate with this function, and we get this function from Meyer-G, and Meyer-G we get from evaluation resource function Meyer-G form log 1 plus z. So this construction can go allow us to separate poles and to build this logarithmic function. So in any case, this is badly constructed Mellin-Barnes integral. We should not construct in such way. We should use here, instead of this, we should use this one and write condition like this one. Okay. So I will show several examples, very simple examples. And now I want to tell that in my own history, I met Mellin-Barnes integrals about 55 years ago, maybe. In my first, during work with my first PhD dissertation. And as a result, I published this book, which was translated from Russian with different name. It was done by initiative of Harold Exton and Lucy Joan Slater. I have contacts with them by letters. They are very remarkable Great Britain mathematicians, well known. Also, I studied, so my first book, you see translation of this book. It's not big one, but I made everything to explain how to operate with this object. And here I placed tables which allow to convert function into these Mellin-Barnes integrals and evaluate integrals from product. For example, this function multiply on this function, convolution of such type produce doable integral, and I gave results for such integrals. So basically, millions integrals hidden inside of this handbook. And later on, I realized this idea in my project together with Prudnikov, Brychkov, and this is Russian version of integrals and series. 5 volumes were published at that time, and 2 volumes translated to Japanese, and 5 it is on Russian, not 3 on Russian. This is republished on Russian later on, and 5 on English. This book, it is very important for me also book. It is Bateman-Ardei, volume 1. Volume 1, Bateman-Ardei book. It describes hyper Meyer-G function, and I studied this using such a book. Also, I was happy to personally meet Professor Vidal Luke, who published 2 volumes about integration, how to work with Mellin-Barnes integrals. And he visited Moscow. We made trip to Central Exhibition with him, met with courses. Then he moved to Riga and tragically died on the way to plane. Plane should deliver him to Minsk. He died in Riga, in Latvia. And later on, I worked with books Masai, Saxena, and then this book, which written by more young colleague of these developers. I did not meet with them, but I contacted by email with Professor Haubelt, who works in Austria. But the major achievement was done, detailed explanation were done by Braxma. He published a huge article, more than 100 pages, with explanation, Mellin-Barnes integrals. And recently, I, together with my courses, published this book in CRC. It includes absolutely unique information about Meyer G and Mellin-Barnes integrals and how to make asymptotics. I gave tables of so-called equivalent for asymptotics. I will tell about this at next lecture, not today. Of course, I should mention research Fox about his name was used for definition Fox H function. And I did not meet with him, but I studied book, not book, article. And now I will tell also about connection with Fourier transform. At last my lecture, I shortly mentioned that we can convert Mellin-Barnes, not Mellin-Barnes, but Mellin transform into Fourier and back. Here I placed collection formulas, and I recommend you to make trip to our collection. It is here in Wolfram function site, and there I placed a lot of formulas for Fourier transform, this Fourier transform, and inverse Fourier transform, and Mellin transform. I will mention the main formula here, and you can verify. I especially demonstrate proof, technological moments connected with this proof. Formula is the following. Mellin-Barnes integral, which I talking, it is inverse Fourier transform from function f in point, this point, logarithm, if function f equal this product. So if somebody like Fourier transform more than Mellin transform, you see inconveniences in operation. Mellin transform is more convenient for operation when you evaluate integrals. Inverse Fourier transform, this one, you know this. And historically, so happened that in our institutes, practically nobody teach that exist Mellin transform, how it connected with Fourier transform. It was ignored. So Mellin transform was rather strongly ignored. This mistake is fixing right now, I hope. Again, I return back to this construction, ABCD in Slater style, and I mentioned that these characteristics is very, very important for this, for Fox H function and so on. They keep information about speed of growing under integrand function. But about this, I will tell later down. Now let's return to Meyer case, Meyer-G case. So we have in mathematical system so-called Meyer-G function. Which was implemented by me about 30 years ago, 28 maybe. Jerry Kuiper helped me in numerical evaluations. Here you see Meyer-G function. It is this function which you saw, but with parameter instead A, B, C, D, you see me, ne, p, and then starting n+1 to p. Crazy construction. Here Q, summation m+1 to Q. So we have continuation from numeration. Also we have bk, we have here 1 minus bk. It sounds very difficult to understand, and I, being student, also was shocked and for a long time did not touch this. And then I studied, found book of Slater, who used this ABCD approach, and everything I understood he teach me, being in English. I was at that time in Minsk, Belarus. So here I described contour. Here we see function which I derived, introduced for using. Why it was happened? It was happened, additional parameter R I introduced. Instead Z in degree minus S, I put Z in degree minus S divided on R. R positive mostly. Because we cannot successfully operate with very important functions without having such parameter. I have example here in notebook, and I will show you. Okay. And this is okay. This is my name, Craziness in Definition Merge. This title I wrote because try to explain people what is it going. If we have this construction, and we immediately memorize that we have this the additional complementary formula for gamma function, and then we can see that we can convert move gamma from numerator to gamma in denominator, and then we also should memorize that gamma function has Stirling formula. Stirling formula, and here I especially wrote three coefficients, three functions: power function, exponential, and I call it super exponential, because this is function which grows much faster than usual exponential function. And if we go to try to look at this formula, we see the following. Here we have this super exponent in numerator, and here this in denominator. So suppose we moved such component from numerator to denominator. And what is it here? Here it is only exponent. You know earlier formulas. So basically, here, if we do similar operations, we should multiply numerator and denominator on the same values, then use above complementary formula, we get this, and then we get this. And here we have nice moment, k from 1 to me, then me plus 1 to q, together, it will be a product from 1 to q. So these guys together produce such product. And here only exponential speed in asymptotics. So here we have exponential speed in asymptotics. Here we have super exponential moment also. And how many? Q minus P. You see, Q minus P. Here, exponential. And also here, everywhere, hidden power. Because if we have, for example, this ratio, asymptotically, it is power in asymptotic. If S goes to infinity. Why I'm talking about this? It is important to understand the following. Gamma function, and its case factorial, is the only function among mathematical popular functions which include three components. super exponential, and power. And altogether, if we multiply them, hidden in Stirling formula for gamma functions, and if we have many gamma functions, like in Mellin-Barnes integrals, they react back together and produce very, very wide set, big set of particular cases. They produce practically all our mathematical functions. This is the list of functions which can be representable through Meyer's G function. Now, you see, Bessel function, I give list in standard form also. Fresnel, cosine integral, hypergeometric functions, Legendre, polylog, Whittaker. No. During my life, I started to collect these functions, and right now we have in computer, in our system, the biggest in the world collection of such named functions and their combinations, because not always just single function. Sometimes we need instead z use other construction like 1 minus z divided on 2 to build Meyer G form from Legendre functions, for example. And we tested this with randomly generated functions, and tests include 90,000 cases involving about 5,000 original constructions, important constructions. And again, in this book, I have about 2,000 only. Later constructions, other constructions I found being in Wolfram research. And this operation can be done if we use command like this one command, resource function. I show, for example, here we can type something like hypergeometric 2f1, then A, B, C, Z, okay. And you see this representation. We can use the following. We can use this divided on this, and it is programming style. Get similar result. And here we can write list No other function 1 minus z. And also we can write here the following construction, which allow us to see what was converted to what. And then we can do something like table form, okay? And then we can make experiment, take something from here. No, you see how it works. Output include inactive merge, but we can make activation. Activate. No, we produce something different, or sometimes coincide, you see, coincide. But in any case, then simplify. No, it become more. No, for example, what is here? Here 1 minus z and here z inside hypergeometric function. And here summation. It is famous formula, by the way. Representation hypergeometric near point 1. Mathematica can do maybe with full simplify, but I will not try to go. And here, maybe this one, I can try full simplify, something like this. Oh. No, I suggest you to play with this. It's a big job, of course. It's very important. And what we have, if we convert functions into mere G, we will have only one enemy to fight with. This is mere G. Difficult, many levels, and right now we have more difficult Fox-H function and similar. But here, what situation? Fox-H in particular include mere G. Let me show this situation. It is here in my notebook, operation with, one moment. Fox-H. No, Fox-H, more information you can read if you go to these links. I have links to corresponding places. And here, interrelations. I collected all this mere G, generalized and usual, and Slater format, and then this format Fox. No, trivially, we see, for example, Meyer G. This is example. If usual Meyer G classical, we need restriction to represent Bessel. But if we have if we have function Fox, this is Fox function, or Meyer G with parameter R equal 1/2, we can represent without any restrictions on argument. This is why I introduced myself about 30 years ago, this parameter R, because we should not live with this one-sided situation when we can represent only through half plane. We should represent for all planes. But Fox appeared recently. And of course, we had experience already, Fox more convenient. Now, I placed rules how you convert Slater to Meyer. You see, we can change variables in such style. If you do this, it can be done automatically, by the way. We can change all characteristics, and rather often people who work with Meyer G see this one. In Slater sense, it is this one. То есть so many difference, how many gamma function in denominator minus how many in numerator minus how many in denominator. And this characteristic connected with power component, as I told. This characteristic connected with exponential component. And this characteristic, this one, connected with super exponential. So we can convert Meyer back to Slater. Also, I gave formulas here. So we made a rather good trip around these Mellin-Barnes integrals, but we did not touch very important questions. How to evaluate this object. No, I will go to this area right now, but before I try to look what I forgot to say important. No, by the way, this I mentioned, yes, life of Lucy Jean Slater. Interrelation I talked about right now. How to evaluate this function. I strongly recommend to go and use my book, because this book, I can provide people who has special interest to get electronic version of this book on English or on Russian. I have also, no, Russian maybe not, but English. And here I made some extraction from the most important moment, how to evaluate Mellin-Barnes integrals. I used also nice notation from Slater. Let's follow me and Slater. Let's introduce such vector. It's not vector, it is in reality sequence. A in bracket, it is component A1, comma, it's equal AA, capital A. Here we have the same construction, but removed term BK minus BK. We remove this and place this. So here we have ratio of product. It means this is equal to this. Oh, it's my fault. I forgot to write this. No, you understand what? Yeah. Gamma. No, maybe I will write here something like this one. It is A. A. Here B minus S, D minus S, minus S, and this C plus S, plus S. This guy is equal to this guy. Control S. Okay. And then we can write in compact manner sum of left residues and sum of right residues in single poles. And below, I will demonstrate how to get these results. And before, I will tell you that there exists theorem 17, which I proved in this book, again, reproved on page 57, this book. It sounds like following. We have Mellin transform, car with star, and then we have the following result. This Mellin transform is the transform Mellin transform from this sigma, which you see above this sigma, or this sigma B. And under corresponding restrictions, this zero you should ignore. It is technological, I think, bug in Mathematica. Just ignore this. So 3 lines. Or we can write function original k. It is this or this or this under corresponding restrictions. And here I made from page 62, 63 of my book corresponding manipulations, which I will not do here, but we come the following estimation of the integrand under Mellin-Barnes Slater form integral, which is the following. And here we should find main term. Main term is the following. Look. S multiply on logarithm S and exponent. This one. Sorry, where it is? Yeah, this one. This guy multiply on this guy. I lost already. Here. This guy multiply on logarithm, multiply on this guy. As a result, we have this is main term. And if we move to left direction by loop, we should check positive or negative this value. It can be positive and provide what provide diversions. If negative, conversions in direction to left direction. But what happened if this coefficient 0? If this coefficient 0, we have situation which you see here. No, I will not detailedly go because it's interesting for all who has interest to this. Now, I will return back and show more examples which we lost in our conversation. Let me return these 6 examples. Yes.
Just so you know, I've been informed that we actually have till 12:15.
15. Yes.
10 minutes.
Yes. 10 minutes. Okay. So here we have examples. I especially selected group of functions. You see, for example, this one, this, and function with unit step. It is kernel Riemann-Liouville-Hadamard fractional integral differentiation. Again, it is special conversations maybe devoted to this. You see here. And what I made here, I made here evaluations that I can return back to logarithm, for example. I used internal command, which we have in Mathematica, command by name Slater form. And you can repeat this, follow me, and get corresponding returning back to these original functions. No, maybe I should finish. Now I did not tell about asymptotic Mellin-Barnes integral, about Meyer G, about Fox. I plan to do this at next meeting with you. But here I say that at the end of this book, we have corresponding information. And we still under developing of new features connected with this area. Thank you for attention.
Thank you, Oleg.
Questions?
No questions from the audience.
No questions.
So
Too specific topic.
I think people are still mulling it over, considering what
Mhm.
you said. All right, if you have nothing else to say, we can finish for the day.
No, I can say, okay, you know, sometimes young people does not know what to do in life. If they have talent, they can go to mathematics to study. It's a lot not done yet in classical mathematics. And as for me, I have 8 PhD students, 3 of them very well-known professor living in different countries. And I am proud in my 77 years that I was able to do such a remarkable job, and I continue to do it. Thank you for attention.